Welcome back, everyone. Today, we're diving into one of the absolute most fascinating challenges in all of tech: how to scale a system from absolutely zero all the way up to millions of users. We're going to be drawing directly from Alex Su's incredible insights in System Design Interview to build out our architecture step by step. By the end of this explainer, you're going to have a crystal clear understanding of how massive web applications actually handle all that insane traffic behind the scenes. Let's get right into it. I absolutely love this quote from our source material. A journey of 1,000 miles begins with a single step, and building a complex system is no different. It's so easy to look at tech giants today and just get completely intimidated by their massive, sprawling data centers. But it is absolutely vital to remember that every single one of them started with a humble, incredibly simple setup. So we're going to start exactly where they did, and we're going to build this architecture out piece by piece. Okay, here we are at day one, the single server setup. Literally everything, the web apps, the database, the cache, it all lives right here on one single machine. When a user on a web browser or maybe a mobile app wants to access the site, they ask the domain name system, or DNS, for the IP address. Think of DNS like the internet's phone book, right? It hands back the IP, and the user's device sends the HTTP request directly to this one lone web server. It's simple, it's elegant, and honestly, for a brand new project, it works perfectly. But of course, success brings its own set of problems. What happens when your user base actually starts to grow? Suddenly, that poor single server is trying to process web requests, run database queries, and manage caching all at the exact same time. The CPU gets maxed out, the memory is completely full, and your application just grinds to a halt. One server is simply no longer enough. So how do we fix this bottleneck? Well, the immediate solution is separation. We split our single server into two distinct tiers. We've got the web tier for web and mobile traffic, and the data tier for our database. Now, why does this matter so much? Because separating these servers allows them to be scaled entirely independently. If web traffic suddenly spikes because of a viral marketing campaign, we can beef up the web server without even touching the database, and vice versa. It's a huge step up in flexibility. Now, since we have a dedicated database server, we have to make a big choice. Do we use a traditional relational database like MySQL or PostgreSQL, or do we go with a non-relational database, often called NoSQL? Relational databases store data in neat tables and rows, which is perfect for complex join operations. But NoSQL, that is incredibly powerful if your application requires super low latency or if you're storing a massive amount of unstructured data. The choice you make here depends entirely on your specific data needs. All right, so we've separated our tiers, but we have to figure out how we actually add power to them. We basically have two main strategies. Vertical scaling, or scaling up, simply means adding more CPU and RAM to your existing server, basically buying a bigger, more expensive machine. It's easy, sure, but there's a hard hardware limit, and it gets incredibly expensive. Horizontal scaling, or scaling out, on the other hand, means adding more individual servers to your resource pool. And let me tell you, for a genuinely large user base, horizontal scaling is the absolute gold standard.
But wait, before we start scaling out too far, we really need to address a glaring danger in our current setup. Even though we separated the web and data tiers, all of our users are still connecting directly to our single web server. What if that web server goes offline? Or what if too many users connect simultaneously and it simply crashes? Poof! Your entire website goes dark. We have a massive, terrifying single point of failure right now.
Enter the real game changer, the load balancer. Instead of connecting directly to the web servers, users now connect to the public IP of the load balancer. Think of it like a really smart traffic cop, evenly distributing incoming requests among multiple web servers using secure private IP addresses. Instantly, boom, our single point of failure is gone. If server 1 goes down, the load balancer just seamlessly routes all the traffic over to server 2. And if traffic spikes, we just throw more servers into the pool. Okay, so the web tier is now robust, horizontally scaled, and fail-safe. We can breathe a sigh of relief there. But what about the data tier? Think about it for a second. We still only have one database sitting there. If that single database crashes, or if there's, say, a localized power outage, we lose all access to our data. We have absolutely zero failover and zero redundancy on the back end. To solve this nightmare scenario, we use database replication, specifically a master-slave model. Here's how it works. The master database handles all the write operations, your inserts, updates, deletes. Meanwhile, we create multiple slave databases that constantly copy data from the master. These slaves handle all the read operations, and since most applications have way more reads than writes, this setup allows queries to be processed in parallel. It drastically improves performance, reliability, and ensures our precious data actually survives even if a server is physically destroyed. Let's take a step back and look at the big picture of where we are now. We've got a highly available setup. The user hits the DNS, gets the load balancer IP. The load balancer then routes to request to an available web server in our pool. That web server reads the necessary data from one of our redundant slave databases, or if a user is, say, modifying their profile, it routes that write operation straight to the secure master database. I mean, compare this to where we started. It is a massive leap forward. So our system is stable, that's great, but as data demands increase, stability just isn't enough anymore. We need speed. Every single time a web page loads, our servers are making multiple, expensive calls to the database. These repeated database calls slow down the entire application, and let's face it, frustrate the user. So the real question becomes, how do we cut down on these heavy database trips to get those snappy response times? The answer is introducing a cache tier. A cache is just temporary storage, but it's much faster than a database because it lives right in memory. We use what's called a read-through strategy. Step 1, the web server checks the cache for the data. Step 2, if it's missing, only then does it actually query the database. Step 3, it saves that expensive database response back into the cache. And finally, Step 4, it returns the data to the user. The next time anyone asks for that exact data, it's served instantly from the cache, totally bypassing the database. It's like magic for your load times. Now, caching handles our database queries brilliantly. But what about heavy static assets? Things like images, videos, CSS, and JavaScript files. Serving these directly from our web servers eats up massive amounts of bandwidth. This is exactly where a content delivery network, or CDN, comes into play. A CDN is a huge network of geographically dispersed servers. I mean, if your main origin server is in San Francisco, a user in Europe shouldn't have to pull a heavy high-res image all the way across the world. The CDN delivers it from a local server right there in Europe, drastically cutting down that latency. The workflow for a CDN is actually incredibly straightforward. First, a user requests an image using a specific CDN URL. Second, if the CDN doesn't have it, it reaches out and fetches it once from your origin web server. Third, it caches that file locally. And fourth, it returns it to the user. From then on, any user in that specific region gets the image lightning fast directly from the local CDN node. Just remember to set proper expiration policies so you aren't serving up stale images or accidentally racking up totally unnecessary data transfer costs. By bringing the cache and the CDN together, just look at how much cleaner this is for our core servers. Static assets are completely offloaded. They go straight from the user to the CDN. Our database is heavily shielded by the cache tier, meaning it only really has to handle unique or updated queries. And our web servers, they're finally free to focus entirely on processing the actual business logic quickly and efficiently. But just as we prepare to automatically scale our web servers up and down based on traffic patterns, we hit a really sneaky roadblock. What happens to user session data? Like knowing that a user is actually logged in. Well, if user A logs in on web server 1, their session data is currently trapped on that specific machine. If the load balancer routes their very next click over to web server 2, guess what? They're going to be logged out. This forces us into using complex, sticky session routing, which honestly makes auto-scaling a total nightmare. And this exact problem brings us to a vital comparison in system design: stateful versus stateless architecture. In a stateful model, server 1 absolutely must remember user A. Server 2 must remember user B. It's rigid, it's fragile. The real solution? A stateless architecture. Here, we extract the user state, the session data, completely out of the individual web servers, and we move it to a shared, centralized data store. Ultimately, a stateless web tier means an HTTP request from a user can be routed to literally any web server in the entire pool. That web server simply reaches out to a shared, persistent data store, very often a lightning-fast NoSQL database, to fetch the user's state on the fly. This shift makes the system profoundly simpler, incredibly robust, and infinitely easier to scale because servers can be added or ripped out without losing a single piece of vital user data. And here it is, our fully scaled architecture. Just think about where we started with that one single server. Now, DNS routes right to a load balancer. We have an auto-scaling, stateless web tier pulling session data from a NoSQL store. Heavy database queries are mitigated by a dedicated cache, and our massive static media is handled globally by a CDN. To ensure ultimate reliability across regions, this entire setup can even be replicated across multiple geographic data centers. We have successfully designed a system more than capable of handling millions of users smoothly and reliably.
But of course, as you'll quickly learn in system design, the journey never truly ends. You successfully scaled to millions of users, amazing. But what happens when you need to scale to 1 billion? Well, you have to push even further. You have to start decoupling your backend services using message queues to handle asynchronous tasks without causing bottlenecks. And when your database gets just too massive to function, you have to use database sharding, literally splitting that massive database into smaller, more manageable pieces. The complexity constantly evolves, but these foundational steps, they remain exactly the same. Thanks for joining me today. Keep analyzing and keep building.